All right, awesome. Right, unfortunately, slightly late start, but hopefully we will catch up to things pretty fast. I think I'll try to leave a good chunk of the last part of the time for questions and kind of some interactions, which is kind of largely the point of this talk. And so I'm going to talk about kind of what we have learned about deploying language models at Entropy over the last 2 to 3 years, since when they reached a size when stuff becomes usable, and kind of also became accessible at a larger scale. And there's quite a lot of interesting things that we'll dive into. I'm also Ilia, a bit about myself. I'm the CTO at Ntropy, also one of the co-founders. Yeah, so let's start with this. So this is kind of like a very cartoony illustration, I guess, of. All right, this actually doesn't skip. All right, cartoony illustration of the reason why a lot of us are attending this conference, right? And the whole purpose, right, is to look at entities and to look at consumers and to look at the exchange of value between the two, right? And on top of that, quite simple information, you can actually build a huge range of products and services, which were really not possible to do maybe a decade ago, right? Everything from like carbon footprint reduction to business finance management, stock market prediction, recommendations, right, risk management, fraud detection, and other things. So all said and done is easy, but at the same time, if we look at this data, there is, even if we have access to financial data or transaction data in some form, right, whether it's bank statements or direct, even JSON dictionaries of transactions or bills, receipts, accounting books, this data is usually very messy, right? And this mess simply comes from the world, right? There is new companies which come and go. There is different countries which have different languages and regulations. Different banks have different standards. And the money itself usually doesn't just directly go from somebody's wallet to somebody else's wallet, which it mostly does in crypto, right? In fiat, there is usually many more parties involved in between that complicate the whole process of understanding and using this data even more. And so if we kind of would be able to, from this whole messy forms of different financial data, be able to make it into a structured form, then kind of we're in the game and we're able to efficiently use it, right? And so the question is, how do we actually convert this messy financial data into a form that's usable by us, right? And this is largely the problem we are addressing at Ntropy with various approaches. And so, so this is kind of like a little bit the lay of the land of what is possible to do with this data, right? So obviously some applications, right, like some PFM apps, maybe some kind of illustrative things are less prone to errors in accuracy, but at the same time they also do require very low cost per data point to be useful, and they also have very high volume and usually also require very low latency. And so for this kind of applications, over the last maybe a decade or two, we have built out a number of approaches to try to understand that data, right? From just lookup tables and databases to hard-coded rules to some small and specialized models to be able to interpret it. On the other kind of end of the spectrum, you have kind of different applications, but usually something around like underwriting large customers, right, or managing the directions of large amounts of money, right, where a simple mistake can lead to massive losses. But at the same time, the value of a success is also pretty high. So this kind of area is also quite suitable for just hiring a bunch of people to look through, like a business applying for a $5 million loan, and you can spend maybe 2 or 3 months looking through their data and evaluating risk appropriately, right? But then stuff in between, right? Like, for example, small business lending or other things, maybe kind of different recommendations we want to do, or some automated account opening, right? Where the volume is very high, you kind of require low latency, but also you really need high accuracy, right? Because the cost of a mistake can still be substantial relative to the value you can get, right? And so here, there's been kind of a little bit of a no man's land, right? Where the application might be very valuable, but there is simply no way to parse and understand data with high enough accuracy at the low enough cost, right? And like hiring a team of loan officers to underwrite, maybe like a $100,000 loan to somebody opening a restaurant is simply not feasible. Simply, if you look at hourly salaries and stuff like that, right? So what do we really do when we want both? But quite recently, this has actually become possible. So yeah, let's just build a better model, right? A model that's both accurate, fast, and cheap. And this is kind of some illustration of how do we do this, right? So when we want to build a model for some financial task, usually we collect a bunch of data. That's kind of the blue circles over here, right? And this distribution of data that we have is our information about how the task looks like, right? As a function of data points effectively. And using that data, we can effectively extrapolate to other data points that we haven't seen, right? And that's usually how any kind of specialized approach works, right? You have some information about how the task looks like, and then you use the information to extrapolate to like unseen instances of that task. However, oh yeah, so this is was also our story. When we started Ntropy around 3.5 years ago, where for the first 2 years, we were indeed building the best model in-house, using larger and larger quantities of data that we collect. Now, this is ultimately what we learned, right? So you can collect a bunch of data, and you can use the data to extrapolate for data points that are similar to the data that you have access to. But then you're kind of always chasing the next wave, and you cannot really just, you're almost there, but then some new customer comes along from a slightly different region using a slightly different bank, and then you have a distribution that is now outside of the distribution that you have trained or fine-tuned your approach for, and then you get errors. So you're kind of always chasing the tail here. Of course, if you have every single data point in the world and you can update your approach in real time with respect to that data, then of course it's fine, right? But it's very hard to get access to data from every single new merchant or company that's opening, and every single bank in the world, and predict every single pattern that's possible. There will always be data that you simply don't know, right, and don't have access to. And so you can get your performance or accuracy to some level, but there will always be this out of distribution set of data points that a new customer can always bring, which can kill your accuracy and ultimately result in a bad product. And so this is kind of another approach to look at it, right? What if we just abandon the idea of trying to chase every single transaction or every single format of an invoice around the world, but simply just take, like every single data point available on the internet and train a massive model on that, right? And maybe, some proxy of the distribution of your task is there, maybe there are some other tasks there, and kind of try to interpolate inwards into your distribution rather than trying to chase the tail of trying to get more and more data. And this is effectively what large language models do, right? You gather as much data from as many different tasks and different distributions as possible. You ultimately shove it into a model, and then that model can be used on tasks that it has seen, but also on tasks that it hasn't seen. And this concept is cool, right? Over the last couple of years, we figured out that it can also be used for financial data really, really well. So this is kind of our story over the last 2 years, where we have been doing really everything imaginable with large language models, looking at different approaches to fine-tune them, looking at different ways to prompt them, do resource-segmented generation, do few-shot learning, and also just try to use them zero-shot with some optimal prompting and chaining. And we found out quite a few surprising things. So this is kind of an illustration of the curve. This is kind of an average across a few tasks that we have seen over the last 2 years. Relatively surprisingly, zero-shot models just out of the box, if they are large enough, can even outperform humans on tasks that they haven't seen. And this is not what we expected initially when we went into this, right? The initial idea was, well, you probably, you can maybe take a model with some pre-trained weights and then fine-tune it on your task, and that should improve it. But what we have seen is that any sort of fine-tuning that you do usually makes the model more brittle for the data points that it's not been fine-tuned on, right? And it can even be more deceptive that you have some eval set, right, where you test things out on, and you take your model and you fine-tune it on some other data points, but because they're still from your distribution, the accuracy on your eval set increases. But then again, we're coming back to this problem that even if you see higher accuracy on your data set, that is actually still not replicated with the accuracy of like an arbitrary customer using your API. And so the most reliable type of model we have seen is simply the biggest model that is as general as possible. So no fine-tuning, no few shots, no examples really in the prompt, just a very concise description of the tasks that you want to solve, and a very, let's say, succinct decomposition of prompts and tasks that kind of step-by-step reasons through what you want the model to do. And so this is kind of some things we have found out, right? So one is that very large general models are very high integrity. What I mean by that is if you test a model on just some few examples, usually its performance on maybe just 10 data points is quite predictive of its performance on any data points from that task. Quite naturally, because this model hasn't seen any data points at all from your task, right? So an out-of-distribution data point and an in-distribution data point is equivalent for the model, right? Because it's not fine-tuned. And so you can get a very kind of reliable pipeline by simply using a very general model. And it's predictable, which is very important. It's also data efficient to use, right? Obviously, gradient descent in machine learning is very inefficient, right? So to train this model is data inefficient, right? But to use it is actually quite data efficient, right? You literally need 0 data points, right? Also a nice property is that if you have built your infrastructure on top of kind of a general reasoning engine, then your infrastructure magically improves when that reasoning engine improves. And your infrastructure will get magically cheaper when that reasoning engine gets cheaper. And respectively also faster when the engine gets faster. And it's also, these models are also so unexplainable, right? There are so many weights that is even able to explain itself, right? Kind of the classic idea in ML was that the simpler your algorithm, the more explainable it is, because you can just go through the code or go through the weights of the model and figure out why it outputs something, right? But here, the model is actually large enough to even explain its own reasoning that actually works pretty well, right? And it actually also helps with even with accuracy. So now, this is still a problem, right? In financial services, there's a lot of interesting things we can do, but very quickly, unless, you know, for some, again, maybe some one-off business underwriting or like venture investments that you can just do it end-to-end with humans, mostly you're very quickly running into cost and latency problems because the volumes are very large, and the whole idea is to extract kind of, you know, usually properties from aggregates of data points rather than from every single data point. And so here, for example, if we want to, this is the cost of kind of enriching bank transactions, right? Which is one of the tasks also we're looking at. The cost of enriching 1,000 bank transactions with an optimal zero-shot pipeline with GPT-4 is about $10 per 1,000 transactions. And the latency to do a single transaction is about 20 seconds, right? Because it involves numerous calls to the model and different things. Now, Visa is processing in the order, slightly under, but in the order of 1 billion transactions per day. And such costs are not really even in the ballpark viable to do this at scale, right? So how do we actually solve this problem, right? Like we have established that for a single data point, we can get something reliable, right? But what we wanted to do is not only to outperform a human on, you know, 20 seconds is also kind of in the order of what a human can do maybe, right? And, right, we want to actually outperform humans on both the latency and cost substantially. So how do we solve these two problems? Well, let's kind of like take a step back and look at what really matters, right? Like what questions are we really asking here, right? Well, one thing that's maybe quite obvious, but sometimes not so obvious, right, is that it doesn't actually really matter, you know, what the cost is of a single data point, right? Or of a single bank statement that you want to, you know, like extract data from, right? What matters at scale is the average cost for all of your data points, right? Or the average daily cost for your daily throughput or something like this, right? Another thing that matters is the worst case data point also usually doesn't matter, right? If you have, you know, like an app with 20 million users, if one of these users has a slow onboarding experience, it's not really going to move the needle. What will move the needle, though, is kind of the classic SLAs, right? Like our SLAs, we usually, you know, we have some P90, P95, P99 guarantees. P100 is usually irrelevant, right? This is kind of the quantile, or P50 would be like the median here, right? And so why don't we just take the model, right, and we attach a cache to the model, and so requests that we have previously sent before, we, store their answers in the cache, and then the next time a similar request comes in or the same request, we just retrieve it from the cache, right? That will obviously reduce our average cost, right? Because some requests will hit the cache, and it will reduce the latency of a certain fraction of our requests, because they will just be retrieved from the cache, maybe in 20 milliseconds rather than 20 seconds. Now, all is kind of clear here, but the problem is these tasks are, very few of them are exactly the same, right? Very few, like invoices are exactly the same as any other invoice. I mean, at least, I don't know, the date and the reference numbers may be different, or sometimes the amount is slightly different for like I don't know, if you're paying out salaries, right? Largely the same, but some parts of it differ, right? So if we simply take kind of a hash of the input and do traditional caching on it, it will work, but we will get very low hit rates on the cache, and so again, this will kind of barely move the needle. So let's dig a little bit deeper from here. So let's do a few more observations. So usually, many tasks that we're looking at in financial services have many subtasks within them, right? Like, let's say you want to do some OCR on an invoice, and what is that task, right? Like, that task is to extract a set of different fields, right? One is maybe the total balance of the account, another one is the account number, a third task is the first transaction, a second task is the second transaction, and so on. And this also applies, to other documents, to entity recognition, and different other tasks we have. Another thing we want to notice is that a lot of the tasks are overdefined, right? So we actually have a bunch of information on our input that neither do we need or are we interested in extracting, and it's kind of just there, to identify maybe this specific data point in some setting. This is like reference numbers, some IDs and stuff like that. Another thing is that a lot of the subtasks that we're doing are actually equivalent to each other, right? If you have a bank statement from somebody who, bought a coffee at Starbucks, and you have the bank statement of the guy who is right behind them in line, then their transactions are probably going to be looking very similar, right? And certain banks have many tens of millions of customers and very similar formats. So with this approach, let's kind of come back to our input and output and a language model in the middle, right? So here is kind of an illustration of what we're looking at in these terms, where the input is actually composed of multiple parts. Some of these parts is simply noise that we don't really need. And the output is also composed of multiple parts. Each part is each of our tasks, right? And so we can take this concept further, and if we have a way to, first of all, identify this noise and remove it, and second of all, to split our big task into smaller tasks, then we can actually illustrate this problem as just running multiple tasks in parallel, right? But of course, we have multiple outputs, so we can now attach a cache to every single one of these subtasks. And so once we have the outputs, of course, we can recombine them into the final output of our task, or which could be like extract all fields from this document. And so, so if we build this out and kind of glue the pieces together, we can. The diagram looks slightly more complicated, but it's also much more powerful. And this is also a general approach that we can apply to various tasks within financial services. and make all of them actually viable at scale with very large and very expensive models. And so this is some benchmarks that we have done and has been actually running in production for almost a year now at Ntropy. So this is a curve specifically for the transaction categorization task of here is a transaction with a bunch of context. What was the purpose of this transaction, or what's the category of this transaction? That's the task. So you can see transaction volume on the x-axis, and the black curve on the bottom is kind of this plain caching. Well, plain actually with some bells and whistles even, where we even mask out the digits and do some simple things. And as I mentioned previously, sure, you can attach simple caches to it, but at scale, it's not really gonna move the needle. But then when you do this subtask caching with task decomposition and denoising and removing the pieces that we don't need, you can get a much higher cache hit rate, and you can extrapolate to much lower P90 latencies and way lower costs. This is another task. This is entity recognition in different kinds of data points. It's a slightly more involved plot because there's kind of different curves for different confidence values of the denoiser, but kind of that's kind of outside the scope of this talk, but kind of the pattern is similar, right? If we versus just plainly caching the input, we're getting maybe something like at the best case 27% hit rate after around 500 million transactions. But then with subtask caching, we can get up to a 99% hit rate, which is pretty cool. And this is some numbers we have observed. So this is from like last 6 months, where you can get some pretty massive reductions in average cost of directly using an LLM pipeline, and also significantly lower P95 latencies. So this is 500x is kind of in the order of 20 milliseconds versus 20 seconds. This is more like 40, but kind of in the same ballpark. And without any sacrifices to accuracy. So this is very worth it, and kind of so ultimately this is one path to bring the power of very large models to the scale we have in financial services, and ultimately extrapolate human level accuracy to a wide range of tasks that we have, and really kind of change the game of what kind of products we can build on top of this. Yes. So this allows us to do cool stuff, and yeah, that's kind of that's the message. So and this is some more information. So so this is a lot more details are in this blog. This is on our website if you're interested in diving through that, and drop me a line at this email. So thank you. So I guess we still have some minutes for questions. Any questions? Yes.
How do you evaluate the accuracy?
Humans. We have internal QA team. We kind of take data from the production pipeline, and then we compare it to kind of a ground truth. And, yeah. But there is for some tasks it's also quite involved, because sometimes there could be multiple ground truths, right? Like multiple labels could be valid here, or there could be ambiguities and stuff like that, right? So, but yes, usually just with humans. Yeah. You're not sure that the explainability, sorry? Yeah, can you, so you're saying explainability is one of the parts, but you're not sure if it's hallucination?
You mentioned that it is sufficiently broad enough that it can explain itself. I mean, the explanation itself is not hallucination model.
Sure. Yeah, I mean, we really treat hallucination as simply just an error, right? It's like, like a wrong category or a wrong field that we extracted, right? A wrong explanation is simply also an error. Way more times than not, it's reasonable and kind of, obviously it's free text, so it's hard to just compare it to ground truth, but with the largest models, it's many times it's very reasonable. Sometimes it's of course a hallucination, but that's, again, we just attribute that to an error of the model, like any other task. Yeah.
You use feedback functions to test the validity of the responses, and have they been useful?
Yes, so this is another thing with kind of decoder only or generative models, is that the output is not really a priori restricted, right? Even if you ask the model to output a certain JSON format or something. What has proven effective for us is we have kind of a pydantic object internally, which identifies the restrictions on the format that you want, right? Like a category has to be from this list. This has to be a valid JSON. This JSON has to have all these fields. Don't use more than, I don't know, 2 sentences for an explanation, all those constraints. And there is another kind of, let's say like error mitigation prompt that if those constraints are not satisfied, it identifies which constraint is not satisfied and starts a conversation with the model. Like, yo, these were your instructions, this was your output, but this output didn't satisfy this specific constraint. Can you correct it? And then the new output we again validate and repeat that loop until it satisfies our constraints. Now, the numbers are something like much worse for smaller models, but for like 3.5 Sonnet, Claude Sonnet, right, or GPT-4o, it's something like only 0.3% of transactions do not actually pass, are not valid after 2 rounds of validation. So it's quite a small amount of data points. Yeah.
Maybe you said this and I missed it, but what does the caching actually mean on the subtask? Like, what are you actually doing?
Yeah, so, well, each subtask, right, is kind of, like extract kind of the organization from this input, right, given this output, right? And so that's a subtask is simply another task. It's kind of just a smaller version of your general task, right? Now, the noise part in the input is just parts of the input that do not affect the output, right? So the decomposition into subtasks we actually do manually, right? So for every big task, we identify what are the subtasks for this task, and then set up pipelines to solve every one of these subtasks, right? Like, let's say you have some transaction and you want to identify all the entities, right? Transaction might have like an intermediary, a counterparty, an account holder. Like, identifying each one of these is a subtask, right? But so this decomposition we just set up manually. And then this denoising part is done with a very small specialized model that we ask it, all right, so basically it's also kind of, it's effectively a version of like named entity recognition, right? Like you can imagine whether a certain party is an intermediary in a transaction doesn't matter if the person name involved is Bob Jones or Jack Appleseed. it will not affect whether PayPal is an intermediary or not. What matters is that Jack Appleseed is a person name, but the actual name doesn't matter, right? It's too much information. So there is a model which basically says Jack Appleseed, person name, right? That's what you need to solve your task, right? You shouldn't care what the actual name is, right? And by applying this principle, we effectively make it, if Jack buys a coffee and if Bob buys a coffee, we can make their transactions look exactly the same, right? Because we replace both of their names with just person name, right? The date with just date because it doesn't matter what date it actually is, right? Stuff like that. So, and it makes things that initially don't look equivalent to be equivalent in a caching formalism.
How complicated is that to add those new caches? Is that immediate, or do you have to design specialized?
No, I mean, this infrastructure is very general. We're using it across a number of different tasks. What you do need to make sure of is, number one, that your subtasks are, of course, dependent on what the problem you're solving, right? Those you just set up manually. And then you also need to have a denoiser which makes sense for your task, right? Like there might be tasks which the actual name of the person does matter, right? Like extract all person names that start with a B or something like this, right? Then of course the name matters, right? So you just need a denoiser which makes sense for your task and just decompose your subtask into parts, right? But that's done only once. So of course you also need the whole infrastructure for caching, right? The databases and a way to, like, sometimes you have like errors in the cache itself, you want to migrate the cache. That is all general and applies to all other tasks. Yeah.
So, have you deployed this in any of the real-time transaction processing scenarios?
Yes, it's been in production for quite a while. Yeah.
Can you give an example of that? During like a PayPal transfer being processed or a credit card transaction being processed, have you applied this?
Yes, yeah. I mean, if you go to Ntropy.com, you create an account, you will, and you start using the API, you will effectively use this infrastructure with LLMs running in the background by default. Yeah, that's kind of. But then, of course, you can measure the latency, on your inputs. You can, right? But yeah, this is deployed at the moment. I think the back was first. Yeah.
I was wondering if you tested open source models and how performance and latency compares to, I know you mentioned GPT-4 3.5 times.
Yeah, we have really tested pretty much everything. And as soon as any new model comes out, we have some infrastructure to evaluate it quite quickly, in particular latency and accuracy. Llama 3 models are very good. Like 70 billion is significantly better than GPT 3.5, for example. 405 is slightly worse than, so Llama 405, right? The biggest Llama 3. The biggest one is still slightly worse than GPT-4, even though I think it's priced about the same. But it's pretty good. Latencies of these models, if it's hosted by some of these open source model providers, right? Like Fireworks or Together AI or something Lepton, usually latency is actually not ideal. We have found that Anthropic and OpenAI and Google Vertex have much more scalable infrastructures. Azure's infrastructure for hosting GPT models is also not ideal. It's quite clunky. Another thing is there's quite little correlation of solving these kind of tasks, which kind of require multiple steps of reasoning and output constraints and all that, versus like MMLU benchmarks, right? Which if you go to like LMSys, leaderboards, right, this general chat benchmarks, there's some correlation, but it's like, for example, GPT-4 Mini is pretty good at chat, right? MMLUs are very high for a model of its size. But at the same time, it's actually quite bad at solving these kind of problems, where you kind of are dealing with data that you don't have so much pre-training on, and then you need to kind of extrapolate and reason about things and constrain your output. So yeah, MMLUs can be pretty deceptive. Yeah, I mean, in general, it's kind of the bigger the model, the safer you are. That rule of thumb more or less applies. Obviously, I guess like this has evolved, I guess, over the last like 3 years in the LLM world, right? Initially, people kind of thought, following this chinchilla optimal limit, right? But then Llama 3 it's actually way overtrained, right? It's like trained on 50x more tokens than the chinchilla optimal limit, and so you can get even more performance. So I guess like either just the model size or the total number of flops that went into its training, which is a function of both the size and the amount of data that it's trained on, right? Those things usually correlate quite well with reasoning. Yeah, something like that. Oh, yeah. Yeah, I mean, it does require a few more queries to Redis and stuff like that to fetch different cache buckets and assemble them together. A lot of them can be done in parallel. Yes, it's more expensive in terms of latency than simply just classic caching, right? Hash, fetch an entry, and just get the value, right? But it's like 5 milliseconds versus 40 milliseconds. It's kind of fine when your SLA is 200 ms, right? It's still in the region of, it's still much less than 20 seconds, right? So, yeah. Yeah.
What kind of thresholds did you use to make sure you're not overtuning? What were the criteria for measuring that you're not overtuning?
Overtuning which part? Well, the training set is only, like these models are not trained, right? They're zero shot. The only thing which is trained is the denoisers that kind of remove information or effectively replace the information with a coarser grained label effectively, right? Now, there we use one parameter which is very important, and that's the confidence score. So if the confidence score of a denoising step is too low, then we don't denoise and we just use the plain text version. So we only remove information which can be removed with very high confidence. That way we don't affect the accuracy. Of course, the lower the confidence threshold, the higher the hit rate, right? Because you can denoise even more, but at some point you're gonna start to rub against accuracy, so yeah. I think we're actually also quite over time, but any more final question? One more. No. All right, good stuff. Yeah, I think let's wrap here. And thank you guys for coming.